Swayam Prabha. Digital India. Educated India.
Hello, welcome to NPTEL NOC, an introductory course on point-set topology. Today we will continue with our study of filters, especially ultrafilters today, module 32. As a easy consequence, today we are going to derive another proof of Tychonoff's theorem. Start with any set. By an ultrafilter on X, we mean a filter which is not contained in any other filter. In other words, in the family of all filters partially ordered by the standard inclusion, ultrafilters are maximal elements. Okay. All atomic filters, Fx, x belongs to x, are ultrafilters. However, there can be other ultrafilters also. You never know. Okay. Remember, this Fx means all subsets of x which contain the little x. If you have one more element there, that means that member does not contain little x. Then singleton x and that member will be, intersection will be empty. That is not allowed. Therefore, Fx is maximal. So that is the idea. So these atomic filters do play a important role. Every filter is contained in an ultrafilter. So this kind of result we are now very familiar using John's lemma. For what we do, start with a filter. Look at the family A of all filters on X which contain the given filter F. This family is partially ordered as usual by inclusion. If lambda is a chain in A, then the standard arguments will give you that union of all members of this chain is again a filter which will contain all of these things. Therefore, that will mean upper bound for this family. Right? Now you can apply John's lemma, there must be maximal elements. Over. As everywhere else, the existence of ultrafilters is assured by John's lemma. But John's lemma is very strange thing. Even though nobody may be able to explicitly display one such, we are guaranteed that they exist. For example, this is not a joke. For example, consider an infinite set and the cofinite filter that you have considered, namely collection of all subsets such that their complement is finite except the empty set. Of course, empty set will not be there anyway. So that is a filter. Okay. Clearly it is not an ultrafilter. Okay, it is not maximal. You can put extra elements there. Okay, of course you have to be careful. But apparently nobody knows an explicit example of an ultrafilter containing it. Okay, John's lemma says there is one. In fact, there may be many, but you won't know, you want to construct one. Let X be any set and F be a filter on it. Then the following statements A, B, C are all equivalent. So we have two different criteria other than the definition which are equivalent to F. So in all we will have three definitions of ultrafilter. Okay. So F is an ultrafilter. The statement B is for every A inside X, either A or A complement belongs to F. Both of them cannot be there, that we know. So this is either A or A complement belongs to F. So this is quite a strong condition. The third one is a weird one, but this is quite helpful also. A and B are in X, the union is in F, implies A or B is inside F. Remember, by the very definition of filters, if A is there or B is there, union will be there already, because any superset will be there. But now some superset is there which is written as union of two subsets. Okay. Then one of them must be inside F. So this is the condition for an ultrafilter. Let us prove this one for some pedagogical reason which will come to know later. I have put this A, B, C in this order. Maybe I should have put A first and then C second and B third. But in my mind this is easier to understand after the definition of ultrafilter. Ultrafilter itself is easy to understand, namely it's a maximal element. It's one of the maximal elements. So that is easy to remember. And then this is simpler and easy to remember also. But while proving, I will prove it in a different way, that is economical. A implies C, C implies B, and then B implies A. That is what we will do. Okay, so first assume F is an ultrafilter and union of two subsets is inside F. First we claim that F union A or F union B has finite intersection property. Okay, if this is not the case, then we get two subsets B1 and B2 inside F. Okay, subsets of X, but they are members of F, such that A1 intersection A is empty. Similarly, B1 intersection B is empty, because each of these family has violated the finite intersection property. Okay, if you remove B, it has finite intersection. If you remove A, it has finite intersection property. So only because you have put A here and B here, it might have violated the finite intersection property, which just means there are members A1 and B1 which when intersected with A and B respectively are empty. But then look at A union B, which is already a member of F, that is the hypothesis here, intersect with A1 intersection B1. See, A1 and B1 are both elements of F. Therefore, intersection is also an element of F. So look at this intersection. This is one element. These two are two other elements. Take the intersection. That is also another element. So this finite intersection, this is nothing but A union B intersection A1. A intersection A1 is empty, so this is just B intersection A1. And then intersection with B1 again. B intersection B1 is empty. So intersection of this finite intersection of this is empty. Okay, so that is a contradiction. Okay, because A union B and A intersection B are already in F. Okay, so it follows that These two have finite intersection property. Any family with finite intersection property will generate a filter, right? So both of them will generate a filter, okay, A intersection B, or one of them, or the one generated by F intersection B containing the other filter. Okay, both of them will contain F. Since F is maximal, okay, this proves that either A must be inside F or B must be inside F. Remember, we said this or this one has finite intersection property, and then assumed that none of them have. That's what we have got this one. So since that contradiction, we get one of them has finite intersection property. We generate a filter which is larger than F, but there is no filter which is larger than F because F is ultrafilter. Okay, so either A or B, at least one of them is inside. Okay, here it's not either A, both of them may be also there, I don't care. So statement only says that see, A or B is inside F. There is no either A or B. Okay, C implies B is one line proof, because what I can do, I can take this A complement as B. Then A union A complement is the whole space X. That's always there, that is free. Therefore, I can apply C to conclude that either A or AC belongs to F. Of course, we know that both of them cannot be, so we can put either A or B. So C implies B is very cheap, right? That is why I proved A implies C first. Now let us prove B implies A. Suppose F is not maximal. Suppose according to this definition, F must be maximal filter, right? That means what? There is a filter F prime containing it properly, right? So take an A inside F prime minus F, a member which is in F prime but not in F. Now C implies AC, the complement, must be inside F, because A is not inside F. Therefore, AC is inside F prime also, right? Because F prime is larger than F, right? Once AC is inside F, AC is A complement is inside F prime. But A and both A prime are inside F prime, that is a contradiction. Okay. So F prime must be equal to F. There is no other choice. Okay. Therefore, we have proved A implies C implies B implies A. The theorem is over. As a corollary, we prove something very important, very useful also. Take any ultrafilter, okay, and take a function from f from x to y, any function. Then f check is an ultrafilter on y. So ultrafilters behave very nicely. No condition on f. Okay, f check. Remember, f check of f is a unique filter which contains f check of A for all A inside f. Okay. How is that obtained? It's generated by those things. Okay. In fact, all that you have to do is take all supersets of f of A, where A is inside this curly f. So that is the definition of f check. So let us see how this comes. All that I have to do is I will use the criterion C. Okay. Or in fact, I can use criterion A here. Which one is I have put here? Actually, I will use criterion B here. See, I all the time think of this as C, but now I would like to think of this second one, A or A complement. Okay. So let B contained inside Y. We have to show that either B or Y minus B is inside F check of F. Take A equal to F inverse of B, that is subset of X. Since F is an ultrafilter, A or X minus A is inside F. Okay, if A is inside F, F of A is inside FF, therefore, and also we know that F of A is contained inside B, right? Because A is F inverse B. Therefore, B is inside F check of. The other case is if X minus A is inside F, then F of X minus A is inside F of F by just definition, set theoretic definition, right? It's X minus A is a member here, F of X minus A is in this family. Okay. Also, F of X minus A is now contained in Y minus B. Therefore, being a superset, Y minus B will be inside F check of C. So we have shown that B or complement of B is inside F check of F for arbitrary subset B of Y, which means F check of F is an ultrafilter. Now, X be a topological space, F be an ultrafilter on X. Then every cluster point of F is a limit point of F. Remember, for a filter, every cluster point was a limit point of a subfilter, right? What is the meaning of subfilter? Subfilter is a filter which contains that, but F is ultrafilter, so there is no larger filter than that one. Therefore, it must be F itself, this F prime which has X as a limit must be F itself. Okay, I repeat, if X is a cluster point of F, earlier you have seen that there is a subfilter F prime. Subfilter means what? Containing F, right? For which X is a limit. But F is ultrafilter, so there is equality here, over. A topological space X is compact if and only if every ultrafilter in X is convergent. So, we have arrived at a very good theorem combining various earlier remarks. So, let me go through all these earlier remarks. 4.40, 7.40, there is a remark. This remark has actually three parts there. Theorem 7.50 and the above theorem, and theorem 7.46, which characterizes the compact spaces in terms of filters. Okay, if you don't remember, maybe I should start just recalling this one. So first let us look at this remark, which says that if F is contained inside F prime, then F converges to X implies F prime also converges to X. Okay. Conversely, if F prime converges to X, then X is a cluster point of F. So this is what just we have used. We will keep using this one again. All right. So next we have this one. Every filter is contained in an ultrafilter. So that also we will be using. Next, we have this criterion for compact spaces, that every filter has a cluster point or every filter has a convergent subfilter, right? And finally, we have just now we have proved this theorem, namely every ultrafilter, then a cluster point is a limit point. So if you combine these things, what you have is start with a compact space and F be an ultrafilter on X. As a filter, F has a cluster point. But just now we have proved that F being ultrafilter, it has this cluster point must be a limit. Okay, so one way is over. The converse is slightly more complicated. Suppose every ultrafilter on X is convergent. Starting with any filter, we can put it inside an ultrafilter G, right? Just now I quoted that theorem. Now a limit of G, because ultrafilters have limits, limit of G is a cluster point of F by remark 7.40 which you have just seen. Therefore, again you apply this theorem 7.46, every filter has a cluster point, so that condition is equivalent to X is compact. So what we have a neat theorem now, a compact set if and only if every ultrafilter is convergent. Okay. Later on we have to improve upon this one. One more improvement is there in a special case. I will come to that one. I am just preparing your mind for such an improvement. Now we will prove Tychonoff's theorem in a very easy way, a very canonical way. Recall what is Tychonoff's theorem? If you have a family of compact spaces, okay, then the product is compact, and conversely the converse part is usually just put for completeness of statements, that's all. That is not part of Tychonoff's theorem actually, because that can be proved much easily, everybody knew that. Okay, namely image of any continuous function, okay, under a continuous function, the image of a compact set, compact space is compact. The projection maps are continuous, so each xj will be compact if the product is compact. That is not what we have to prove. What our aim is, if xj's are compact, x must be compact. Okay. So what we shall do is, every filter on this product is convergent. Okay. For each j, look at pi j check of f. Just now we proved that pi j check of f is an ultrafilter on xj, right? But xj is compact, so it converges to some point x little xj inside xj. Okay. Now it is a matter of just to easily verify using the product topology here that this point x, whose jth coordinate is xj, is a limit point of f. Okay. See what you have to show a limit point. The neighborhood of this one is contained inside f. That is the meaning of a filter converges to x, right? Converges to that point. So maybe I will leave this as an exercise to you. Okay. I mean, there is not much exercise, but you have to write down the detail, that's all. Unlike the case of topologies, it is easy to determine all filters and ultrafilters on a given finite set. You might have known that the study of finite topologies is indeed not a part of point-set topology at all as such. It is maybe number theory, combinatorics, all sort of things are there. It is quite a different flavor, different kind of things. And as far as topologies are considered, to some extent it provides some counterexamples, that's all. Beyond that, topologies don't use it much. But the problems are there, and it is easy to find problems, but difficult to find solutions here, of course. Yeah. So here, similar questions, if you ask for filters, and then you can combine them also. So I am going to tell you one single thing, namely counting the number of filters and ultrafilters on a finite set. That is very, very easy. So okay, suppose f is a filter on x is a finite set. Then you can take intersection of all its members. That must be a member of f, right? Of course, it must be non-empty because it is a finite intersection. and it follows that that member B is contained inside every other member, which just means that F is FB, the atomic filter. Once B is there, all supersets are there, everything is there already. So F must be FB, atomic filter. Okay. So every filter is like that, means what? There is a 1-1 correspondence between subsets of F, subsets of X, and filters on X, except B equal to empty. So if you throw away the empty set, you exactly have 2 power n minus 1 elements, the number of filters on it. Similarly, let us look at when is this filter an ultra filter. That is also easy. The moment there are more than 1 point, it won't be ultra filter, because I can take a smaller one, namely singleton B here, for example. That Fx will be contained inside this. Fx will contain this one. So there are larger filters, right? Therefore, the only ultra filters are FB, where B is singleton. So how many singletons are there? Precisely n elements. Over. Okay, so that is just for your flavor. But I just want to, I am myself not an expert in this kind of things. I want to ensure that there you can find many interesting questions here, but answers will not be easy. On the other hand, if X is infinite, then the answer is much more difficult anyway. We do not know all the filters nor or ultra filters on a given set. Just take infinite, in particular take a countable infinite set, natural number. Even there we don't know. As observed earlier, we do not know an explicit example of an ultra filter which contains the cofinite filter on the set of natural numbers or any countable set. So one more remark here. Suppose a filter contains a subset B, then obviously the atomic filter is contained inside F. Okay, because F contains all supersets of B. Suppose further that no proper subset of B is contained inside F. See, F may have even smaller subsets, right? Then what happens? Given any A inside F, B is there, A is there, A intersection B is there. But A intersection B is not a proper subset of B, just means that B is already contained inside it. Therefore, F must be FB. Okay. Alright. As a special case, assume that F contains a finite subset. Then clearly we can choose B to be such that cardinality of B is the smallest. Okay, amongst all finite subsets contained inside F. It follows that once you choose that smallest cardinality, just cardinality is smallest, it follows that F must be FB. So you can't have several B such that all of them have same cardinality. Okay, that's also clear anyway. So in particular, we have proved that every ultra filter which contains a finite subset must be an atomic filter. Okay, so this is something I would like to say, some trying to understand what are ultra filters and so on an arbitrary space, on arbitrary set. Okay, so the darkness is still there once you don't have this hypothesis, namely a filter which may not contain any finite subset. Then you won't know how to characterize them. Okay. So let us stop here. Next time we will study ultra closed filters.